Thank you so much. Thank you for including me in this. So I'm going to tell you about this paper that's joined with Kirill Rudolph, who's a former student, currently a postdoc at Berkeley, and my colleague Fedor Sandomierski. So going back to Nash's Princeton dissertation, what you see is what we all know of the paper and the thesis. It introduces the concept of a non-cooperative game and develops methods for mathematical analysis of such games. It also analyzes a three-person poker game, which I always found kind of odd because it's a very weird example. And just in case you think I'm making this up, I actually dug up the dissertation. This is the front page. And here is the one-page abstract. I extracted the middle. So the first paragraph says what we all know and love. The last paragraph says is an illustration of the possibilities for application. A treatment of a simple three-man poker model is included. By the 1951 paper version, it switched to a three-person poker model. But either way, it's a little bit of a bizarre example. Now, some of what I'll show you today will actually connect to this example. So we'll link back to this part of it. But overall, we're going to link Nash equilibria to correlated equilibria. So correlated equilibria were formalized by Bob Aumann in 1974. They generalized Nash equilibria to allow players to correlate their actions. And they capture pre-play communication, intermediation, joint randomization. They also result from a natural learning dynamics that perhaps Sergio will talk about next. And they're efficiently computable, which is a great feature that perhaps some people will touch upon later in the conference. So the broad question we're asking here is, when is there potential value in correlation? This is a very vague question. I'll be more formal in what I mean by potential value. So just to put this in context before I go to the details, correlated equilibria are equivalent roughly to the outcomes that result from adding a recommendation system on top of the existing interaction. So in many ways, what we're asking is what interactions can be improved by a recommender system. Alternatively, correlated equilibria are equivalent to outcomes from arbitrary pre-play communication protocols. So one way to think about the questions is what strategic interactions are susceptible to such pre-play communication or collusion that's done through communication. And the main message that I'll try to convey to you is that correlation is potentially valuable for Nash equilibria that entails sufficient amount of randomization. That will be the main message. Okay, so here's what I'll do to you in the next 30 minutes or so. I'll be more precise about extremality and improvability. Then most of the time I'll focus on conditions for improvability. Then I'll tell you about translations to payoff space, namely utilitarian and Pareto improvements. And if we have time, I'll show you an application to symmetric games, kind of constructing beneficial correlated equilibria explicitly. All right, so I'll start with the basics. I know this is familiar to everyone. We see it basically in every talk, but just so that we're all on the same page with notation. A normal form game is effectively a triplet of a finite number of agents. N is the set of agents. A finite set of actions for each player I, which is denoted by A for actions, sub I. A will, then without a subscript, will correspond to the entire set of profiles. And a utility for each agent that maps a profile of actions to a payoff. A correlated equilibrium is a distribution over profiles of actions that satisfy these linear incentive constraints. So one way to think about these constraints is that you have a mediator who generates this distribution. And for each realization, they give each player a recommendation of what to play. And it better be the case that each player is best responding by following that recommendation. That's this incentive constraint. So each individual, when receiving the recommendation to play action A sub I, they get at least as much as playing any other action. Okay? Hopefully this is clear to everyone. Okay. Now, Nash equilibria are a subset of correlated equilibria, and they take a very particular form. They're product distributions, because each individual can only randomize independently. So the real contribution here is that we're allowing for correlation. Now, the set of correlated equilibria is a very nice set. It's defined by the set of linear incentive constraints. This is why it's easy to compute. And it's a convex polytope as a consequence. And a polytope is a convex hull of its vertices or extreme points. So this is what will play an important role to us. And we'll say that a Nash equilibrium is extreme if it is an extreme point of the set of correlated equilibria. Okay, so again, the set of Nash equilibrium is a subset of the set of correlated equilibria, and we're asking when is a Nash equilibrium an extreme point of this superset. Okay, and I'll soon explain why it matters. So our question is, when is a Nash equilibrium extreme? Now, I started out by talking about improvability and benefits and all that, so what's the connection to extremeness? Well, think about maximizing, say, a linear objective over a polytope P. So this is one depiction of such a case. For generic objectives, the optimum will be achieved at a unique point, which is an extremum of the polytope. Right? And for non-degenerate objectives, you might get kind of the picture on the right. So, in fact, Bauer's maximum principle tells us that generically any linear, for example, utilitarian, or convex objective attains its unique maximum at an extreme point. So this means that non-extreme equilibria are generically improvable. You can always find some objective that will improve upon them. Now, this is a pretty conservative notion of improvability, because we want improvability by any objective, any generic objective. So at face value, it seems like this is a very demanding condition. And what we're trying to show is that, in fact, there are many equilibria that satisfy it. Okay, so let me give you the main result, the first main result at least. So if you're going to remember one result from this talk, please remember this one. And here's the result. It says that in a generic n-player game, a mixed Nash equilibrium is extreme if and only if at most 2 players randomize. So this is a complete detail-free characterization of extreme Nash equilibria. So it doesn't depend on the number of players in the game or the structure of the strategic interaction. It just depends, the sole relevant statistic is the number of people using mixed strategies. Now, if you don't like this genericity, this is a technical detail, but you can discard of genericity and focus on regular Nash equilibrium, and the same result will hold. All right, so, yeah.
Question?
Yeah?
Is this imply that in 2-player game, any Nash equilibrium is
That's right, that's right. And I will soon, give me 2 bullet points and I'll get there. Yeah. So what are some implications for this before I show you some intuition? First of all, pure equilibria are extreme. Second of all, if we have a unique correlated equilibrium, this means that we have some structure on it. It means that it has to be, quote unquote, almost pure. We can't have too many people mixing. And as Rita said, it also suggests that equilibria with exactly 2 randomizing players are extreme. And this is, in fact, where the literature stood till this paper. We have a few papers that show that Nash equilibria are always extreme in 2-player games. This kind of gave the feeling that this might be a universal truth. But in fact, it's very special to the 2-person case. Now, if 3 or more players randomize, any generic objective can be improved, either by introducing correlation or by switching to a different equilibrium that entails less randomization. And so, as I mentioned, 2-player games are not representative, And furthermore, if you think about symmetric equilibria, which hopefully I have a few minutes to talk about at the end, if there are 3 or more players, any mixed symmetric equilibrium is going to be improvable. Okay, yeah.
There's something I don't understand, because imagine a two-player game where all the pairs are 0.
If all the pairs are 0?
So everything is generic.
Yeah, so that's not generic. Yeah, that's exactly what we're ruling out.
Whatever example somebody gives, it's not generic.
But that's in a way what the regularity takes care of as well. Yeah.
But the zero-sum game is also not generic because it imposes a special relationship between the pairs, correct?
That's right. That's right.
So
So that's why we switched to regular equilibria, because we thought genericity might rub people the wrong way, and it does. All right, so I'll do the intuition in 2 steps. I'll first give you an example that just illustrates what's different between 2-player and 3-player games, and that will bring us back to Nash's seemingly weird example, which in retrospect perhaps is not that weird. And then I'll give you a slightly more, an intuition that's slightly closer to our actual proof. Okay, so let's think about a version of the game chicken that Alman suggested. So this is a game of chicken. We have 2 drivers. They each prefer to play the other person to play safe, and they are willing, and the best thing for them is to play risky when the other person is playing safe. So just to remind you what we teach to our undergrads, there's a mixed Nash equilibrium here, which is 50-50, and it solves a linear equation. So it's basically, we nail this 50-50 based on the indifference condition. The indifference condition only depends linearly on the probability P that the other agent is using the risky choice. So it's a linear formula. Now, what Alman showed was that you could shift weight from the risky profile into the other 3 profiles, thereby increasing utilitarian welfare. Now, the mixed Nash equilibrium, as Rita pointed out and I just said, is in fact an extreme point. We're talking here about a 2-player game, and I'm not going to use the genericity excuse. Why is it an extreme point? Well, you can think about an objective that maximizes the weight on the risky and safe profiles, and there actually the mixed Nash doesn't do so poorly. Okay, now let's shift to a 3-player version of this. So we're adding a driver.
That's equivalent to the 0, 0, 1, 1, 1, 1, 0, 0 game, right?
Again?
Why don't you use that? Yeah. It's strategically equivalent to 0, 0, 1, 1, 1, 1, 0, 0. Right.
Yeah.
It's much easier to understand, but never mind. Okay.
That's almost originally.
Yeah,
Okay.
okay.
I'm going to show you my example, which has 3 drivers, and we're just going to extend it to a symmetric game, and we want to maintain these incentives where you want the other players to choose the safe strategy, and the worst thing for you is if everyone chooses risky. Okay. Now, the whole point of this, you can choose Sergio and Bernard. You can use a different example if you prefer. But the point of this example is that there's a symmetric mixed Nash equilibrium that has these irrational numbers. Now, this is really the link to Nash, because in Nash's example, there are also irrational numbers. And that was kind of strange that they emerge even though the payoffs were all integers. Now, why does this happen? Well, now when we write the indifference conditions, each player has to consider all the possible combinations of play of other players, and so it's going to be a quadratic equation in this probability P that each of the other players play risky. And the solutions of a quadratic equation might be irrational, right? So in fact, if you have more than 3 or more players, the indifference conditions are generally not linear. Now, if we think about extreme correlated equilibria, now we have a system of linear equations where all the coefficients are integers. So the extreme points have to have rational numbers. So in particular, this sort of example already illustrates to you that with 3 or more players, we have a potential for a mixed Nash equilibrium to be non-extreme. Okay? Now, this is a very particular example. Maybe we can add Sergio's example to it, but we want to show this in general. So, so here's the general proof intuition. So the very, very high level idea is that when we have many players randomized, there are just too many ways to coordinate their actions. And one of them is going to be beneficial. So I'm going to focus on a particular example to illustrate to you what's driving this. So think about a game with n agents where each one has only 2 actions. So binary action game. And I'm just reminding you here that if mu is correlated to the equilibrium, it must satisfy these incentive constraints. So again, whenever a person is told to play action AI, it must be the case that they wouldn't benefit by switching to a different action AI prime. So this means that each individual who mixes in this correlated equilibrium, who plays both actions with positive probability, has 2 constraints. Otherwise, they'll have only 1 constraint. So at most, we have 2 times n constraints. Now, what Winkler told us is that if we have k linear constraints that are imposed on the set of all the distributions over action profiles, then the extreme distributions have support of at most k plus 1. So this means that the support of an extreme correlated equilibrium is at most 2n plus 1. Okay, so now let's think about a Nash equilibrium. So suppose that nu is a Nash equilibrium with k agents mixing. Recall it's a binary game, so the support of nu contains 2 to the power of k action profiles, right? Each agent has 2 actions. So if there's any hope that nu is extreme, it has to be the case to 2 to the power of k is less than or equal than 2n plus 1. Right? That's the 2n plus 1 is the bound we found from Winkler in the previous slide. Now, in fact, we can replace 2n plus 1 with 2k plus 1 by eliminating non-randomizing agents, effectively replacing them with dummy players. So therefore, our restriction is that 2 to the power of k is less than or equal to k plus 1. Now, on the left-hand side, we see something that grows exponentially with k. On the right-hand side, bless you, we see something that grows linearly with k. And you can convince yourself that this equation holds only for k equals to 1 or 2. Just plug in k equals to 3. So the conclusion is that in this case, in this binary game case, if we have more than 3 mixing agents, it cannot be extreme. Now, the same argument or very similar argument applies to equilibria where players mix over the same number of pure actions. Where it becomes a little bit more challenging in the general proof is when some players mix over a much bigger set of actions than others. So that's where the proof entails some somewhat more involved arguments. Okay, so far what I tried to convince you is that with this agnostic perspective, where we're not committing to any particular objective, improvability is quite prevalent. Now you might say that usually we use very particular objectives, that's all we care about. And utilitarian welfare or Pareto are best-selling hits in this select group of objectives that we often think about. So this is what I'm going to shift to next and ask essentially the same question in payoff space. So this is what we're going to do. So we're going to use the extremality approach as before. So the set of correlated equilibria, again, is a subset of all the distributions over action profiles. And the set of all distributions over action profiles is a set of dimension that corresponds to the cardinality of each action set multiplied by one another. Now, equilibria are often represented via the payoffs that they generate, and that corresponds to a set in Rn, right? The payoff for each of the n agents. So a much smaller set in general. So we'll say that a Nash equilibrium is payoff extreme if its payoff vector is an extreme point if its payoff extreme, if its payoff vector is an extreme point of the set of correlated equilibrium payoffs. Okay? And you can hopefully already see that this ties to improvability in objectives that depend on payoffs, much in the same way as what I started out with. So what we want to understand now is what can we say about payoff extreme equilibria, and then also think about utilitarian objectives and Pareto dominance. So proposition, in a generic game, a Nash equilibrium nu with more than 2 agents randomizing is not payoff extreme. And furthermore, its utilitarian welfare can be strictly improved. So utilitarian welfare, the sum of utilities. And if you like weighted welfare, that's fine too. You could do any weights you'd like. Okay, so let me give you a partial intuition for where this is coming from. So the correlated equilibrium payoffs are a projection of correlated equilibria to a lower dimensional space, this Rn. Now, extreme points of a projection are a subset of the projection of extreme points. Try saying that 20 times. Just in case this is not crystal clear, let me show you stuff in a picture. And this geometric analogy will be quite useful for us. So think about this cube and the shadow it's casting depending on the different directions. Now, in the generic case, the shadow it will cast will look like a hexagon. This is what it will look like. And notice that in the generic case, each of the extreme points here is mapped to a unique extreme point of the cube. But some extreme points of the cube are mapped to the interior of the hexagon. Right? That's the idea of the subset. Now, in non-generic cases, when we project the cube in a very particular direction, we'll actually get a square, and we'll get this weird case where 2 extreme points are projected to the same extreme point of the shadow. This is a non-generic case, right? In the generic case, each extreme point of the shadow is sourced by a unique extreme point of our cube. So this is exactly what happens in our case. So what we show is that in a generic game, each extreme point of correlated equilibrium payoffs corresponds to a unique extreme correlated equilibrium. So let's consider a Nash equilibrium with more than 2 agents mixing. We know that it's not extreme from the first result I showed you. Now, in a generic game, if it's payoff extreme, it has to map back to an extreme correlated equilibrium. Contradiction. Okay. Now, Pareto improvability is much more demanding than utilitarian improvability because we need all the players to be better off if one outcome dominates the other. So it shouldn't come as a shock that we have more stringent condition for Pareto improvability. So in fact, the last true result that I'll show you today says that in a generic game, any Nash equilibrium with at least 3 plus log 2 of n plus 1 mixers is Pareto dominated. Okay? Now, the precise formula here doesn't matter for our purposes. So one thing that's interesting here is on the one hand, you need way more mixers than for plain improvability. On the other hand, it's a vanishing fraction. If you looked at large games, it's a vanishing fraction of the population that has to mix for an equilibrium to be improvable. And in fact, we can show that a Nash equilibrium that satisfies this condition can be strictly improved for all agents.
Improved by a correlated.
Sorry?
Can simply be improved by a correlated equilibrium.
By a correlated equilibrium, which means either a different Nash equilibrium or something that uses correlation non-trivially. Okay, so I'll give you a really hand-waving intuition for this one that's based on these pictures. So again, correlated equilibrium payoffs are in Rn. Now I'm going to say a really long sentence and then show you a picture. So for a generic projection of a polytope to an n-dimensional space, the interior of n-dimensional faces are mapped into the interior of the image. So let me show it to you in a picture. So here's our cube again with its shadow. And what I'm saying is that if you look at stuff that belongs to the interior of a face, it's going to be projected to the interior of the shadow. It's never going to be projected to an extreme. Sorry? Generically. Generically. Okay, so where does this come from? This term of 3 plus log 2 of n plus 1 just guarantees for us that in a generic game, the Nash equilibrium belongs to a face of dimension at least n of the correlated equilibrium polytope. Okay? So that's where this number is coming from. All right. So in the few minutes that remain, I'd like to show you kind of one application to symmetric equilibria and show you a technique for actually calculating explicitly a correlated equilibrium that improves upon the Nash equilibrium. Okay, so I'm going to show you how to construct these improving symmetric correlated equilibria. And the main idea, if you don't want the details, is that we're going to use the Finetti idea of presenting an exchangeable distribution as a mixture of IID distributions and some convexification techniques that we all know and love. And in the paper, if you look, I won't have time to talk about applications precisely, but this is applied to congestion games, voting games, protest games, and a few others. Oops. Okay, so let me show you just an example to illustrate this. So let's think about binary action games, which we already discussed. So n agents taking an action from 0, 1. If you want an example in your mind, you can think about taking route A or route B, voting or not voting, going to protest or not, and so on and so forth. And now we're going to normalize the payoff from action 0 to 0. Some applications you might not want to do that. That's fine for the techniques, but this will simplify the exposition. Now, the payoff of any player I is going to be 0 when she takes action 0. That's our normalization. And if she takes the action 1, it's going to be some function of other agents taking the action 1. Okay? So if you think about congestion games, for instance, my value from going on a new road depends on the fraction of others who are going on that new road as well. And we'll assume that if everyone is taking that new road, then that road is not appealing. Okay, so f of 1 is negative. And we'll focus on large population behavior. Okay, so the first observation here is that all agents' equilibrium payoffs at all Nash equilibria, pure, not pure, symmetric or asymmetric, converge to 0 as n goes to infinity. So asymptotically, all equilibria generate a per capita utilitarian efficiency of 0. So how do you see that? Well, what I'm showing you here is this function f, the payoff from action 1, as a function of the fraction of agents choosing 1. So notice that in the shaded areas, the payoff from choosing 1 is strictly positive. So anyone who's choosing 0 would have a benefit from deviating to 1. And in the blank spaces, kind of over here, the payoff from choosing 1 is strictly negative. So anyone choosing 1 would benefit from deviating to 0. So the only points where this doesn't hold is exactly at the intersection points. And in fact, the bold ones on the downward intersections correspond to stable equilibria. Now, okay, so now I'm going to show you very briefly how to find improving symmetric correlated equilibria. So in principle, this is a hard task because we have an arbitrary distribution over all action profiles. So this is something that has 2 to the power of n minus 1 parameters, so a lot of parameters. Now, De Finetti's theorem is truly awesome because it tells us that we can restrict attention to a mixture of IID distributions. And in fact, we can show, and I'll soon, hopefully the figure I'll show you soon will kind of give you a hint as to why this is the case, that we can consider only mixtures of 2 IID distributions. So the optimization problem that at first blush looks very difficult can be translated into this optimization problem. So we're maximizing the expected value of x times f of x. So x is the fraction of people randomizing, and each one of them gets f of x, the payoff from choosing 1. So, sorry, x is the fraction of people choosing 1. And in principle, we need to take care of 2 incentive constraints, that when you're told to choose 1, that's beneficial, and when you're told to choose 0, that's beneficial. As it turns out, the first one is satisfied for sure. I'm not showing you this because it's kind of standard. So we're left with one constraint that corresponds to the constraint that if you're told to choose 0, that is your best response. Okay, so I'll just want to show you one figure and then we'll end. So we can draw a graph that corresponds to the results of utility from an atom on X. So if we only got everyone to randomize with and choose 1 with probability X, then the utility would be X times f of X. And the incentive constraint here would be 1 minus x times f of x. Okay. So now I'm going to show you the figure that corresponds to these 2 terms. Now, in principle, we can use any convex combination of this. So in principle, we can implement the convex hull of this black graph that corresponds to the graph that I just illustrated to you. So once we use this convexification, you can immediately kind of see where is the optimum. So we need the incentive constraints to be non-positive, so it's only the shaded area that's relevant. And then we want to maximize W star conditional on the incentive constraint holding, so within this triangle that is shaded, that corresponds to W star, which is on a line connected by 2 dots. So that's why we can use only 2 randomizations. Okay, so let me conclude, and I'll leave a few minutes for questions. So as a conclusion, there are several papers out there that effectively show the extremality of Nash equilibria in very particular context, and this is not even a comprehensive list, but it goes to various types of competitions, patent races, first price auctions, convex potential games, 2-player normal form games. And what we show is kind of that in general, what the unifying theme here is that there is a tension between randomness and extremality or improvability. And it's a detail-free criterion in a large set of settings. So that's all, folks.
Question. There are many games that have the same set of correlated Nash equilibria, namely games that are strategically equivalent. Namely, for example, in two-person games, you subtract a constant from all the payoffs in the same column of player one, which sounds crazy, but it's correct. Okay, that doesn't change the mixed best reply of the players. Now, when you look at the Pareto result that you had, suppose that I'm asking the following slightly different question. Look at the Pareto improvement for some utilities that are consistent with getting exactly that set of correlated equilibria. Maybe you can get rid of the log n there.
I see. Nice. Okay. I
mean,
that.
just a wild conjecture. I have no idea why this, but it's a constraint. It's a weaker constraint than what you had, and maybe you can get it with less randomizers. Yes. And again, as I said, for example, just to say, the example that you get from Aumann, which looked very complicated, hard to follow, if you do this strategic transformation that does not change anything in the game, you just get a very simple game, 0, 0, 1, 1, 1, 1, 0, 0, and then all the arguments become very clear.
So
it's a pity people don't do that much more.
Oh, no, you go ahead.
Well, thanks. I just have two questions. One is, so if I understand correctly, any extreme point among the set of correlated equilibria will have at most two people who randomize independently, in the sense that they...
no, all we're saying is that if you start with a Nash equilibrium that has more than two people randomizing, it's not an extreme point of the correlated equilibria. The correlated equilibria in principle could have more people randomizing. But if there are more people randomizing, it's not going to be a Nash equilibrium.
Nash equilibrium is still a correlated equilibrium in which everyone's randomizing independently.
Yeah, but not every correlated equilibrium is a Nash equilibrium, right? So you could, in principle, have correlated equilibria that are not Nash equilibria, that are, yeah?
Second question is, in the more general case of the incentive-compatible mediation plan a la Myerson with incomplete information, then you have even more...
That's right. So we have some results. It's not complete, so I'm not presenting it, but we have an almost proof that then the restriction is much more severe, and in fact, whenever you don't have a pure equilibrium, it's improvable. Yeah.
We can take